Hi everyone, and welcome to the first of this week's sessions where we're going to be exploring characteristics around speed and acceleration. And then in the second session this week, we're going to actually look at how we can develop speed and develop acceleration within athletes. So start to explore some of the training methods we can employ to actually develop these characteristics within the athlete. But first, through this session, we're going to try and explore some of the physiological basis of speed and acceleration. So looking at the physiology and what underpins our ability to operate quickly, so in terms of max speed and acceleration. We then start to understand the actual characteristics of maximum speed, so what determines maximum speed, and as well start to develop an understanding of the characteristics of acceleration. Before we get going, it's important that we get a good understanding of some of the key terms that we're going to be using when we're talking about speed and acceleration. So when we're understanding the characteristics of speed and acceleration, but also when we're looking at how we can train some of those characteristics as well. So one of the first terms is the rate of force development. So this is the time it takes for us to develop a certain level of force. So it might be how long it takes to develop maximum force, or the amount of force we can develop within a set time period. Okay, so sometimes the rate of force development is a bigger determinant of our ability to move quickly than our absolute ability to develop force. And we'll start to explore that a little bit as we go through. The next is impulse. So this is the product of the force generated and the time required for its production. So if we looked at a graph and we saw the level of impulse, okay, the height that it would reach in terms of the absolute force, the impulse is the area that sits under that curve. We also need to differentiate between some of the terms that we use in terms of speed and acceleration. Sometimes we often use these interchangeably, but there are subtle differences across some of these terminology. So the first, obviously, is speed, and this is just how fast an object is moving. So its rate of movement, and this tends to have no kind of directional element to it. Whereas velocity does have a directional component. So it's how fast something is moving and the direction that it's moving in as well. And then finally, acceleration is the rate at which an object's velocity changes. So for a person sprinting, it's the rate at which they can change their velocity over time. Now, before we can explore the characteristics of speed and acceleration, how they differ, we want to get a good understanding of the physiological underpinnings for speed and acceleration. And the neuromuscular system together is key for developing speed and acceleration. Okay, it's not just the strength of the muscle or the ability of the tendons to return some elastic energy, for example, but the ability for the nervous system to activate the muscles quickly. So if we get an improved neural drive and an increased rate and amplitude of impulses to the musculature, then that's vital for developing speed and developing acceleration. So if we can get signals to the muscle faster and get an increased firing rate within the muscles, then that's going to lead to overall increases in speed and acceleration. And another key mechanism that we need to be aware of for developing speed is the stretch shortening cycle. So this coupling of the eccentric and concentric actions of muscles, okay, leading to a rapid response in the musculature. So we can tap into this stretch shorten cycle to be able to perform actions rapidly. And as I've said, the stretch shortening cycle is this coupling of the muscle contraction. So the eccentric concentric coupling of muscle contractions whereby the muscle tendon complex is stretched rapidly, and then from that initial stretch there is a rapid shortening immediately after. So what this does, it taps into the intrinsic characteristics within the muscle tendon complex and this force length feedback that we have within the nervous system. So we can imagine the muscle tendon complex being somewhat like a spring and allowing us to store elastic energy. So the more stretch that we can apply to the muscle tendon complex, the greater amount of elastic energy that is stored within that complex. Now, it's important that for any rapid movement, we want to go from the lengthening of that muscle tendon complex to the shortening as quickly as possible. The longer the time is from the stretch to the shorten, the more elastic energy is going to be lost. So we can't store that elastic energy indefinitely. So that's why for any rapid movement, this stretch shorten cycle needs to be extremely quick. So that's why we compare it often to like a spring-like mechanism. And we get a stretch in and then a rapid shortening, utilizing that elastic energy within the muscle tendon complex. And if we look at an example of utilizing the stretch shorten cycle, we can see it here in this figure from a jump. We can see that in that early stance phase, so as the foot is planted, we go into the eccentric phase of our stretch shorten cycle. So we get an eccentric loading of the musculotendinous complex, and we're starting to build up elastic energy within that complex to be later used in the concentric movement. Okay, so as we load through this eccentric phase, we then get essentially a transition phase, which is known as the amortization phase. And ideally, we want this phase to be as short as possible during any rapid movement action, because the longer that we stay in this phase, the greater the dissipation of elastic energy that is going to occur. So we want to go from the eccentric to the concentric action as quickly as possible. And the longer we stay in this foot plant phase, the amortization phase, then the more we're going to lose some of that elastic energy that we're building up during the eccentric component of the stretch shorten cycle. And we can think of this in a different way as well if we compare a counter movement jump to a squat jump, for example. Counter movement jump, we make use of this eccentric loading of the stretch shorten cycle as we dip down into the jump before exploding up. Whereas in a squat jump, we go into a quarter squat position, we hold that position, and then we get a dissipation of that elastic energy that we build up in the eccentric phase of the squat. And we can see how that manifests in different jump heights. Typically, we'd have much lower jump height in the squat jump compared to the counter movement jump. So we can start to see how this stretch shorten cycle can really improve our ability to perform actions quickly and powerfully. And now one of the key components we have to think about within the muscle that relates to the stretch shorten cycle, not just obviously the musculotendinous complex, obviously loading a lot within the tendon. Okay, that can store a lot of elastic energy within that tendon. But we also have to think about some proprioceptors as well. And one of the key ones we have to think about for the stretch shorten cycle is the role of the muscle spindles. So these spindles wrap around muscle fibers, and what they do is they monitor the changes in the muscle length, and they can sense any rapid stretching within the muscle itself. And if they sense a rapid stretching, then the motor neuron linked to the spine will cause a reflex action within the muscle spindles themselves. So this is a protective mechanism to prevent overstretching of the muscles, okay, to prevent damage. So with a fast action that taps into this mechanism, we can utilize the muscle spindles to help limit the stretching and therefore cause a shortening of the muscle, so that we can then go into the concentric component of a movement. Now, if we move slowly through a movement, then you're not going to get activation of these muscle spindles. So they're activated during rapid movements, which obviously with any movement that is powerful or trying to be a fast movement, okay, we're going to get an activation of these proprioceptors, and we want to tap into that during the stretch shorten cycle, so that we can go from a rapid stretching to a rapid shortening of the muscle. And the quicker we can do that, the more powerful the action can be, or the quicker the action will be. So, as I've said, the proprioceptors in the muscle, in particular the muscle spindles, play a key role in limiting the overstretch. We also have the Golgi tendon organ, okay, which feeds back as well to the neuromuscular system about changes in length, changes in joint angle, and the tension within the muscle itself. And we'll explore that a little bit more as we go into third year. But principally, we want to activate the stretch reflex response from the muscle spindles to prevent this overstretch, so that we can get more rapid actions. Okay, so we can get more powerful movements and faster movements. Okay, so we want to tap into this physiological mechanism whenever we're performing an action that utilizes this stretch shorten cycle. So in order to utilize this and activate this, then we need to make sure that our movements are quick and can tap into this system. So now we've looked at the physiological underpinnings related to speed and acceleration. We're going to actually look at the characteristics now of max velocity, speed and acceleration, and see the subtle differences between the two. And then that will feed in going into the next session about how we can train for those different characteristics. Now, when we think about speed, we need to think that our ability to move quickly within a running movement anyway is due to an interaction of both stride length and stride frequency. Okay, and typically, obviously, if we increase either stride frequency or stride length, then you should see an increase in overall speed. Now, what we can see in this figure here is that for early increases within overall speed, okay, we can see going from 4 meters per second up to 5 meters per second, the increase in overall speed comes from a change in stride length, okay, in those early phases of increasing our overall speed. And then as we increase our stride length, we're also seeing an increase in stride frequency, but in those early stages of increasing our speed, so typically through an acceleration, we will see that the greatest increase in our speed is due to a change in stride length. And this continues, okay, we can see in the figure going up to around 6 meters per second, still an increase in stride frequency, but again, a greater increase in overall stride length. But then as we increase our overall speed, as we start to head towards maximal velocity, and this is obviously from a rather high level sprinter, you can see in terms of their speed that they're able to achieve, we can see that as we start to near top speed, the role of stride length starts to decrease and stride frequency starts to be the main driver between any increases in overall absolute speed. So what this should be showing you is that depending on where we are within our running, so whether we're in an acceleration phase or whether we're in a maximal velocity running phase, that will indicate what is most likely needing to change in order to increase the overall speed at any particular point. So in the early stages, when we're accelerating, the greatest increase in speed comes from a change in stride length. But then as we start to near top speed, any further increases in our overall speed is going to come from the change in stride frequency. And obviously this starts to then be a fine balance between these two metrics. We could continue trying to increase stride length, but we would see a detrimental impact on overall stride frequency if we try to extend the stride length too long. So there's a fine balance between the two. And similarly, if we see that just increasing stride frequency to increase any more could potentially lead to a significant decrease in stride length. So depending on the phase of the running, okay, is going to impact on what is needed to be changed in order to increase our speed at any point. And one of the key factors as well we need to think about, as we kind of mentioned briefly earlier, is this idea around rate of force development. Okay, so the ability to develop a certain amount of force within a particular time period. And if we can develop the same amount of force in less time, then typically that would result in an increase in overall speed. And we'll look at that in a little bit more detail as we go through. Now, if we're looking to develop absolute maximal force, then that can take from easily around 300 milliseconds up to around 800 milliseconds. Okay, and as we'll see in a moment, that can have a significant impact when we're thinking around sporting actions. Now, what we can see in this figure here is that even though certain athletes might be able to develop higher absolute force levels, okay, as we can see in the purple dashed line, which is the heavy resistance trained athlete, at a lower time point, so around 200 milliseconds, the actual force that can be developed by an individual who is explosively trained or ballistically trained will be much higher than the heavy resistance trained individual. So their rate of force development is much higher in the individual who is ballistically trained or explosively trained. Okay, for that same time point, we can see that even though the heavy resistance trained individual would still get a higher force than the untrained, okay, that's still much lower than the explosively trained individual. So therefore, if we want to have a greater force or rate of force development, then we need to think about how we can train for that so that we can train explosively. And that 200 millisecond time frame becomes important when you start to think about different sporting activities. So here we can see a breakdown of different sporting actions, okay, and the time available for force application. So this very often would be ground contact time. So we can see that for sprinting, ground contact time would be 0.08 to 0.1. For long jump, about 0.1 of a second. High jump a little longer. Javelin delivery, shot put delivery, even the hand takeoff for vaulting, all have time frames much shorter than that 200 milliseconds. Okay? The only one that we can see higher is something like the vertical jump. Okay, but very often in most sporting actions, the key factor is going to be how long the ground contact is, okay, or how long the actual contact time is when performing an action. And if you can develop a higher rate of force in that same time frame, then that's going to mean that you can get a more explosive action or a quicker action compared to anyone else. So when we look at the differentiation between acceleration and maximal velocity running, we can look at the impulse that's left during the foot placement during running. Okay, so we can see that during landing, okay, so this is in the acceleration phase, we get a rather high braking impulse, followed by similar propulsive impulse, okay, in terms of the vertical force, and with still relatively high horizontal force. Okay, but biggest component is around vertical force. Okay, and we'll look at why that vertical force is important as we go through. But you can see that we get a rather rounded shape in this overall trace from landing. So that early part is the landing phase, the braking impulse, followed by the propulsive force. And when we compare that to the maximal velocity impulse that we see from the ground reaction forces during max velocity running, we can see that in this braking phase, the early phase, the vertical force is a bit higher in that first braking part as the foot lands, and then we get a still relatively high force overall, vertical force in the propulsive phase. But importantly, we can see that the overall ground contact time is significantly shorter during the max velocity running. As you can see that the impulse finishes around 0.1 of a second, whereas compared to the acceleration impulse that we saw in the previous slide, where the ground reaction time was somewhere around 0.14 to 0.15, which may not seem like a huge amount, but can be quite significant when we're trying to perform an action as quickly as possible. Okay, so we can see there's much higher braking impulse that we're having to overcome when we're in max velocity running compared to the acceleration phase. So when we think about acceleration, we're obviously thinking about the rate of change in velocity, okay, or the increased speed or rate of movement. And typically when we're thinking about sport, this would normally refer to distances around 5 to 10 meters. But it can actually take anything up to 20, 30, even 42 meters to reach maximal velocity. Now, vast majority of sports, most of the time, there's not going to be much opportunity to run those kind of distances to get to maximal velocity. Okay, so there's going to be probably a greater focus on that ability to get up to sort of 20 meters, because that's going to be then a bigger focus on the acceleration phase. Now, we can see within a 100-meter race, though, for example, that for an Olympic sprinter, so this is a breakdown of the velocities for Usain Bolt during his 9.58 world record. And we can see that in the early acceleration phase up to around 30 meters, so we get that early drive phase where we're increasing velocity. Okay, so we see as a percentage of max velocity, about 73%, and then we're increasing that up to around 30 meters, 40 meters, where we start to enter into the maximal velocity stage. Okay, and it's from that 40 to 60 meter phase where the high level sprinter, so an elite level sprinter, would be reaching maximal velocity. And then in those last 40 meters, it's a focus more on speed maintenance. Okay, so we start to see a slight decline in the overall maximal velocity that is being achieved in those later stages. Okay, so there's actually a relatively short time period within the race where they would be able to get to maximal velocity. Being able to sustain it for kind of any longer period becomes quite difficult. And whilst it only seems like a small drop off, which it is, kind of those 1-2% drops can make a significant difference in overall time to completion. So when we're thinking about acceleration, we're thinking from most sports perspective up to 5-10 meters, but depending on the sport, it could be up to around 30 meters as well. And when we think about the characteristics for acceleration, typically, so if we're sprinting, around 10 meters, sprint velocity would be around 8.2 meters per second. Ground contact time a little longer, so around 0.17 of a second. Stride frequency around 3.64, and the stride length is around 1.5 meters. So you can see relatively shorter stride length in those early stages, but relatively high stride frequency. But we see longer ground contact time as we're trying to apply greater forces to the ground in order to accelerate up to maximal speed. And the actual ground reaction forces that can be going through the body at this time during the acceleration phase can be anything up to sort of 7 times body weight that we're subjecting the body to. So there's a lot of force going through the body during this acceleration period. And in terms of trying to maximize our ability to accelerate, there is an important focus on the positioning of the body. So for a sprinter, for example, one of the key features we need to think about is this triple extension at the hip, at the knee, and at the ankle. And that movement is really important for a lot of sporting actions, okay, but we see it particularly here, okay, where we got the angle of the body is around 45 degrees from the floor, and we see a straight line effectively from the shoulder all the way down to the ankle. We start to see any deviation in that angle, for example, so we see a drop here, we're not getting full extension through the knee or through the hip, then we start to lose the ability to apply force. We're not maximizing the force that can be applied through the ground. We're not making the most of it. So we want to see, for any person trying to maximize acceleration, this straight line all the way from shoulder to ankle with the triple extension as they're driving during this acceleration phase. Now, as we're obviously driving off, we get that triple extension on the one leg. We actually want triple flexion on the opposite leg, okay, with a relatively low heel recovery, okay, keeping that relatively low to the ground, but we're flexing at the hip, at the knee, and at the ankle, ready for the next step, okay, so that we're primed, ready for that triple extension in the opposite leg as well. Okay, so we're getting it into an ideal position and ready for the next foot plant. We also want a neutral position of the head, okay, and the spine. We start to see the head go down, then we're going to get a curving of the back, and we won't get this straight line, so we're getting an inefficient application of force into the ground. And similarly, if we're facing too far up, we're going to be becoming upright too quickly. Okay, so during this drive phase, this is the type of positioning we want to be getting in to maximize our ability to accelerate. And we can see as well a positive shin angle there, ready to facilitate this triple extension through the knee and ankle. And if we look at the velocity within the first 10 strides from a run, we can see that around 70% of max velocity can be achieved within roughly 6 strides. Okay, so we can see a significant shift. So from the blocks, okay, we've got about 4.2 meters per second, and then by step 6, we're up at around 8.4 meters per second. Okay, and then we can see how it's just a more gradual shift in the increase in velocity, okay, over those later stages of the race. And then when we look at how this translates with ground contact time, we can see that in the early stage of the race, we're getting significantly longer ground contact times in comparison to the later stages of the race. So as we are increasing the velocity, okay, as the athlete goes from kind of more horizontal position, and we're getting that 45-degree lean, okay, and as they start to become upright, Okay, we start to see that the ground contact time keeps decreasing until we reach our maximum velocity, where our ground contact time is at its lowest. So what this should be highlighting is that with acceleration, if we want to develop acceleration, we can afford to have slightly longer ground contact time in order to enable for the development of slightly higher overall absolute forces. And it's those development of slightly higher absolute forces which allows us to increase our acceleration before we get into the maximal velocity running stage. So for many sports, we can think of acceleration as possibly being more important than absolute speed. And that's because in the vast majority of sports, either the space doesn't allow for developing maximal velocity, or it just the actions within the game mean that there are fewer opportunities for maximal speed, maximal velocity to be achieved. And so very often developing acceleration capabilities can be more important from a sporting perspective. And as we've mentioned, the ability to accelerate is dependent on this interaction between stride length, stride frequency, and the ground contact time. Okay, but most importantly, it's about the relative force that can be applied in that time. Okay, so we can see in this comparison here between a fast group and a slow group, examining their kinematics during acceleration, we can see that there is a significant difference in horizontal hip velocity overall, but there's not a significant difference in stride length. Okay, but there is a difference in stride frequency, and that stride frequency is facilitated by shorter ground contact times. Okay, we can see that in the actual flight foot time, so left and right foot, there's no significant difference between the two groups in terms of how long their foot is in flight, but their time of ground contact is significantly different. So what this suggests is that for the fast group, they are able to apply either similar or slightly more force in less time. Okay, and whilst there is a slight difference in stride length, it wasn't significant, and its stride frequency and the rate of turnover, which is the biggest determinant here, and their ability to apply force, okay, in a shorter time frame. So if they can apply the same amount of force but in a shorter time period, then that's going to lead to a greater ability to accelerate. And now if we think about maximal speed characteristics, okay, so when we're thinking about maximal speed for the velocity around 10 meters, max speed could be anything up to about 12.8 meters per second. So that's for kind of elite level athletes, elite sprinters. Their ground contact time is significantly lower. So anything about 0.08 of a second, slightly higher stride frequency, and also slightly longer stride length. Okay, obviously once we're into maximal running, we get a different body position, which is going to enable slightly longer stride lengths to take place. And again, if we look at some of the similar data to what we looked at before, but at the latter stages, so 10 steps and into the max velocity whenever we're running, you can see again significantly lower ground contact times as we start to reach maximal velocity. And so whenever we're trying to operate at maximal speed in terms of running, then there's a number of kind of features we need to think about. There's a number of characteristics we need to bear in mind in order to achieve kind of maximal velocity. And from running, we need to make sure that our shoulders are sitting over our hips, which in turn stay over the feet, during the stance phase, and our center of mass is within that stance as well. So we're not too far forward, we're not leaning back. Similarly as well, we want to make sure that our head remains stable, okay, and that the shoulders are relaxed and that they're going through the same turnover speed as the legs as well. And what's important as well to try and think about is that we want as much stability as possible. We don't want lots of rotation. We don't want lots of kind of tilting left to right, because any movement, whether that be rotational or leaning side to side, is going to lead to a loss of energy. So energy is being wasted in those movements and it's not being put into kind of our horizontal movement. And we'll look at that in a moment when we actually look at a bit of analysis of Usain Bolt's running, okay, and some just different things sometimes to think about and that we can adjust when we're trying to coach and train maximal speed characteristics. Now, one thing to mention is the difference that we can see across different levels of athletes. Okay, so we can see in this figure here that for our elite athletes, we're seeing both an increase in stride length, so up to around 2.7 meters per stride, okay, and a step rate of around 4.6 per second, and nearly 4.7. So whilst it may not seem significant difference, so we're seeing around about 15 centimeter difference in stride length and around about a 0.2 difference in step rate, then what that then manifests though is a significant difference in overall speed. So as you start to get more elite level, the stride length can increase as well as the rate of turnover as well. So now we're just going to have a little bit of analysis of Usain Bolt when he ran his world record, the 9.58, and just highlight some of the sort of positive and negatives that we can maybe pick out in his actual running technique. Now, it's important to note that it was very often thought that someone of his height wouldn't be able to be successful at the 100 meters because he's around 6'5", and many thought that that would be too tall, that in this early phase of the race in particular, wouldn't be able to get the leg turnover speed in order to be able to compete. Now, obviously, Usain Bolt's been able to prove all those wrong. That's not to say that the way he runs is absolutely perfect, but we will just have a little look at kind of some of the things that we can think about when we're thinking about both acceleration and speed, and in order to develop those elements. So we can see in this early phase we're not seeing much movement laterally as he runs. All the energy is going into moving him forward. We can also see that at this point, whilst many would have thought that he had a lower stride frequency, he still had similar step rate to many of his competitors, and he was still level with many of his competitors even after sort of around 10 meters. And again, we can still see that here. He's still level with many of his competitors. And then one thing that is often not seen is that as he runs, we can see that there is some deviation in his legs. So we're seeing some internal rotation, okay, from the knee, which is obviously going to lose some energy. So it's not ideal. He can compensate and he's able to adjust the movement in the upper body to compensate for this internal rotation. But it's just highlighting that there are some issues, and this is probably as a consequence of having just such long legs and needing to accommodate that limb length in a relatively short space. So not having enough space to work with is leading to some of that internal rotation. So there is some loss of force as he's applying the force in those early steps, in those early strides, but there is some counterbalancing with the movement of the upper body and a bit more rotation. But fundamentally there is still some loss of force during this action. And then as we move through, you can see the rest of the race. Okay, we scroll through. Okay, now if we start to look into the biomechanics here, we can see that he's got a nice high knee lift as he entered into that max velocity phase. So even though he may not be renowned or be able to have the fast start of others, the fact that he was level and at the kind of 30-meter point, he could then enter into a much greater maximal velocity as he went through sort of 60 and 70 meters, enabling him to pull away from many of his competitors. And now his long limbs facilitate a long stride length, and that doesn't come at the expense of the rate of turnover either. So he's getting a nice high knee lift, he's getting upright, there's not a particular lean forward, okay, and he's able to continue to maintain that maximal velocity as we enter into the latter stages of the race. And you can see him here again, just significantly longer stride, and there is still some movement through his shoulders, which isn't ideal. Partly this is because of some scoliosis in his back, so we're actually seeing him lose a fair amount of energy because of the movement of his shoulders. So we don't get a stable movement as he's running. Okay, but you can see that he's able to keep a center of mass, and within the stance, he's not going above it, he's not kind of falling forward. Okay, so he's able to apply a lot of force down into the ground, and there, that's where he's applying this stretch shorten cycle within the legs. Okay, so he's able to maximize that elastic energy and then convert it into the to the forward horizontal movement. Okay, using that the vertical force that can be generated from this stretch shorten cycle. You can see here as well, like I said, this center of mass stays relatively stable. Okay, and behind that front leg. So therefore he's able to increase his step rate along with his increased stride frequency. Okay, and here you can see as well we're getting that triple extension, okay, through the hip, knees and ankles, and a good knee lift. Okay, foot is ready to plant for the next stride. Okay, so that we can then extend through those hip, knees and ankles for another long stride. Okay, so you can see how this utilization of that movement is really important, of that triple extension, okay, even when we're at maximal velocity. So having good mobility, okay, around the hip in particular is really useful and beneficial for sprinting. If you're limited in your movement, if you can't get particularly high knee lift, then you're not going to be able to get much extension either. Okay, so being able to have a good flexion extension around the hip, but also in the other joints, the knee and ankle, is really important. Okay, also the fact that he's able to stabilize, we're not getting significant variation or oscillation in his hip height. Okay, it means again we're not losing energy. Okay, he's not losing significant energy, bouncing up and down. That's staying stable, and it's his legs that are moving around this kind of central point. Okay, so like I said, we do see some movement in the shoulders, which isn't ideal, but he makes up for that with other factors. So we do see a slight forward body tilt, okay, enabling us to get that extension through the lower leg, through the leg as a whole. Okay, and we're able to then utilize that momentum that's been developed. Okay, keeping a stable trunk, okay, and not having too much movement or rotation where we're going to be losing energy. Okay, and finally, just this ability for shoulder mobility as well is really important. So being able to get good movement, we're not limited, okay, within that joint range. If we start to see a limitation in that, okay, that can impact on the stride frequency or the stride length. So having good shoulder mobility is really important as well, and generating further momentum as we're driving the arms forward. And finally, just wanting to have a little look at the interaction of some of the metrics we've looked at and the overall relationship with running speeds. So if we look at the figure at the top here, we can see at the lower speeds, the increases in speed were primarily driven by increases in stride length, okay, at the lower end. And then as we increase speed, the further increases were as a result of increases in stride frequency. Then if we look at the second figure here, so B, we can then see that as we increase overall speed, so as the overall speed increases, we see a decrease in both ground contact time and in swing time as well. So the actual swing phase during the stride also decreases. So we're getting a faster rate of leg movement and of leg turnover, as well as that reduction in ground contact time. And then finally, we can see that we see both an increase in impulse and overall force going through the body in direct proportion to the actual speed as well. So particularly force increases in direct proportion to the running speed. Okay, so whereas we see with impulse, it increases from this slower to intermediate speed, but we start to see a decrease at maximal speed. Okay, but still that increase in overall force going through the limbs. And so just to finish up, some key take-home messages, just recapping what we've gone through today. So acceleration and speed are as a result of this stretch shorten cycle, so this rapid change from an eccentric to a concentric action. Okay, that underpins our ability to accelerate and to operate at max velocity. Acceleration is characterized by greater overall ground reaction forces and longer ground contact time in order to be able to generate those greater absolute forces. Whereas max speed is characterized by greater vertical forces and shorter ground reaction times. So if we want to develop our acceleration abilities or our max speed abilities, then we obviously would need to take these things into consideration. We'll start to look at that a little bit more in the next session. Okay, so that brings this first session where we're looking at speed and acceleration to an end. As always, if you have questions, please get in touch. I'm happy to answer any questions you have. In the next session, we're going to be exploring how we can actually train to develop speed and acceleration. So we're going to apply some of the knowledge we've developed in this session and the characteristics of speed and acceleration, and use them to apply to the training methods that we might use if we're trying to develop those characteristics. So thanks for listening, and like I said, if you have any questions, please feel to get in touch. Okay, cheers.